to our last lecture for alkanes. Before we start, if you recall, before the holidays, the lecture before the holidays, we actually talked about this checkpoint 2. And I think at that point in time, many of us are very confused, as in how is it related to your checkpoint 2A, because that molecule there doesn't have a chiral carbon, if you recall that. Correct? And then I think someone in the LT actually asked the question, and it got everyone very confused. Okay, so after that I went to read the question again. If you look at it, 2A is actually not related to 2B. 2B is actually asking for the simplest alkane that will be able to display a chiral center. So it has nothing to do with 2A. So the answer is still valid. Okay, the answer is still valid. So the simplest alkane that can exhibit optical activity is actually a carbon, is actually a molecule with 7 carbons. Okay, so that question is still valid. The answer is still valid. Okay, so for those who have not taken down the answers the previous time, maybe you'd like to take this down, because the question is asking you to identify the simplest alkene while we wait for our friends at the back to settle down. So what we're going to do today is to finish up the alkanes lecture. Thereafter, there is still one more topic to carry on. It is the alkenes, and that lecture will take 3 lectures. So for camerats, I guess many of you, none of you would have collected the notes. So please go and collect notes from the photocopying lady tomorrow afternoon, from tomorrow afternoon onwards. Okay, so please take note, all the camerats. Go and collect your lecture notes from tomorrow onwards. Tomorrow afternoon onwards. Okay? So, this one settled. Let's move on to the lecture proper today. Excuse me, I think I need your attention. I know you have not met your friends for 1 week. You are very excited to share with them your holiday stories. Okay, all the horror stories or all the wonderful stories. Please leave it to break time. It is lecture time now. I think you know how I work. I need a silent LT and I need you to listen as well. Let's cooperate. I don't think you want to be scolded on the very first day of school. Thank you for your cooperation. Let's move on. So in alkanes, like mentioned, there are a few, in organic chem we have quite a few mechanisms that we all need to know. So we will get to learn one by one over the 2 years. The first one that you'll be learning is actually the free radical substitution. If you recall the last lecture, which is before the holidays, I went through the fundamentals with you. I go through with you what is homolytic fission, what is heterolytic fission, and we talk about radicals. So in this case, we are putting that into use today with a free radical substitution. Okay, so free radical substitution will involve alkanes reacting with a halogen. Okay, in the presence of UV light. So what will happen is that you will get alkyl halide, or you will get RX plus the HX. Okay, so as I, oops, what happened? Okay, so the conditions needed is that your UV light is required, homolytic fission is involved, whereby the bond will break, each party will get back its own electron, and it is actually a fast reaction which occurs rapidly in the presence of UV light. So I need the UV light, okay, in order for me to have this reaction occurring. Okay, so if I use methane as an example, reacting with a HX, okay, I will have X replacing one of the H, okay, then I will form a HX. So if I react with more, okay, oops, the H will be substituted. And then if I react with more halogen, then more will actually react. So can you see that if I react with X2, I'll have one H being substituted. As I react with more, okay, I will have 2. And then if I react with more, I will have 3. Okay, so the substitution goes step by step. Yeah, is there something to do with the connection? Okay, and then I'll have the last one. Okay, let's try. Hopefully it doesn't flicker. So multiple substitution can occur. I can have a mixture of product depending on how much X2 that I actually placed inside. Okay, so like I mentioned, you can start with a mono substitution, but as you put more and more of the X2, if the amount of X2 is actually more than the methane, you can actually have a poly substitution. Okay? So for a large proportion of mono substituted products, if I want a large proportion of a mono substituted products, I will use a large excess of the RH. Because if I have more methane, like in the previous case, as compared to the X2, mono substitution will occur. But if I want to have a large proportion of the poly substituted, that means to say I want to have more than one H being substituted, I will use more of the X2. Okay, so this is how you can work it out. If I have more X2, limited of the RH, I will have a poly substituted products. Okay, this is the big idea. Later we will go into the mechanisms. Finish? Move on. So the reactivity of the X2, okay, X2 we all know is a halogen. Okay, this is the reactivity order. F2 is the most reactive, followed by Cl2, Br2, and the last one is actually the I2. Okay, for free radical substitution, we will deal with Cl2 and Br2. F2 and I2 is not used in this mechanism. Okay? Because it is very explosive in the dark, and this one is too unreactive. Okay? So when we talk about free radical substitution, we are mainly talking about Cl2 and Br2. So for the mechanism itself, there it involves 3 steps. The first step is the initiation, that means to start the reaction, that means the formation of your radical. Initiation. The second step is the propagation. This is the step whereby you get all the things that you want, whether is it mono substituted or poly substituted. The last one is the termination. Termination is whereby the reaction will stop when 2 radicals come together, terminate. Okay, so this is initiation, propagation, and termination. Where I'm referring to now is actually on page 8 of your lecture notes, so you can just follow closely. Okay, the mechanism as well as the write-up is actually at the side, so you can read while I go through. Okay? So the first part, the first step is actually the initiation. Initiation means to start. So to start, going by the name, I have a free radical substitution. Meaning to say, for a start, I need to generate the free radical first. So to generate the free radical, I need to break up the Cl-Cl bond. Whoops. Okay, I need to break up the Cl-Cl bond. So note, last lecture, we also talked about homolytic fission, whereby it is a fishhook arrow, and each species will just take back its own electrons. Okay, so this is the first step, the initiation step, whereby there is a free radical, there is a breaking of the Cl-Cl bond. Okay, maybe I give you 2 minutes now, you read while we settle this IT problem. Okay, so 2 minutes, please read your page 8. Okay, I give you 2 minutes to read. Can you please read through? So that you get some idea before we go through. Okay, are we good? Okay, so you have briefly read through the description as well as the different equations. So let's go through it now. I repeat again. So there are 3 steps: initiation, propagation, and termination. So given by the name is a free radical substitution, we will need to produce radical first. So the first step is the initiation, whereby the Cl-Cl bond is broken, okay, by a homolytic fission. So this is a fishhook arrow. If you note, this is not a full arrow, this is a fishhook arrow. We will get the 2 radicals. So after getting the radicals, what will happen? We will go on to the second step, whereby the propagation will take place. So the radical itself will react. In this case, I actually use the scenario of an ethane. Okay, so it will react with your ethane, whereby this radical will come near the ethane molecule and one of the bond will break. Okay, so one of the CH bond will break and you will form a HCl molecule. With the formation of the HCl molecule, okay, with the formation of the HCl molecule, you notice that this molecule here has become a radical. Okay, so looking at the bond energy itself, okay, 431 and 340. Okay, so you will note that you will actually have a radical form here. So this is just an animation graphic to give you a better understanding. Next, then you have this radical. So this radical now, okay, because it is a radical, so it will react with a molecule. Okay, it will react with a molecule. So in this case, the molecule is your Cl2 molecule. So you will form your chloroethane. So if you form my chloroethane, you note there is another radical that is being produced. So when the radical is being produced, the story goes on. Okay? The story goes on. So I have my initiation, whereby I form my radical. I have my propagation, because at the very start, I only have a Cl radical. So the Cl radical will react with the ethane molecule, forming a radical, and the HCl. So then this radical that is formed will have to react with a molecule. So the molecule that it reacts with will be the Cl2 to form your chloroethane with the release of a radical as well. Okay? Then the Cl is regenerated again. So then now we go on to the third steps. If the reaction is going to go on, okay, over time you will notice that there will be less and less molecule, more and more radical in the mixture itself. Okay, so over time, termination will then occur. Termination occurs when I have two radicals meeting each other. When the two radicals meet, they will just form a bond. And when I form a bond, in this case, it happens to be two ethane radicals meeting each other. So at the end of it, I will form a butane. Okay, there are many other possibilities whereby you have two radicals meeting together. Okay. So I also can have, if I have my two Cl radical meeting together, then I will form back my Cl2 molecule. Okay. So actually I have a lot of different possibilities of the radicals meeting. Okay. So what you need to take note in this mechanism is step 1 is the initiation. You need to have the radicals itself, and in order for you to have the radicals, you need to supply energy. It's by heating or by UV light. Okay, because when energy is supplied, you break the Cl-Cl bond or you break the Br-Br bond. That's where the start of the reaction will occur. There will be all the radicals available, and then you can start the reaction whereby the radical will react with a molecule, and the chain reaction can just carry on. Okay, when there is more and more radical and less of the molecule, then the radicals will just meet, and that's where the reaction will stop, and that will become your termination. Okay, so it goes in 3 steps: initiation, propagation, and termination. Okay. So this one is the overall summary of it. Okay, then you ask me what do I need to show in my in my mechanism itself. Okay, what you need to show is the initiation. You need to write the title: initiation, propagation, and termination. Okay, the 3 steps so that people know what you're talking about. Okay, as for the fishhook arrow here for the ClCl, okay, there is no need for you to draw. There is no need for you to draw the fishhook arrow. Okay, you just need to show me how you get your radical. Okay, for the propagation part, you will need to look at the question. You need to see what the question asks you. Is the question asking for mono substitution or poly substitution? If it's a poly substitution, then you will need to carry on to show your examiner till the product that they want. Okay, if not, you can just show 2 steps to show the propagation, how the Cl is being substituted in. For the termination, okay, you can just write any of the 2 that is occurring. Any of the 2 equations to show your termination will be good enough. I hope you have taken that down, because I don't think I wrote it inside my notes. Okay, this is the propagation. Many things can happen, so you just write 2. You know this is mono, this is actually poly, this is also a poly substitution. Okay, so it very much depends on what the question wants. If the question wants you to substitute 2 Cl, then you will need to go on further. From this part, you will need to go on. If the question only asks for mono, then you can just stop here. Okay? Clear? So let's try out. Let's try checkpoint 5. Okay, see if you can apply what you have learned. Please refer to page 8 if you are in doubt. Shall we carry on? I hope you get a sense of how to write the mechanism. So first one, I have my fluoropropane and 1,1-difluoropropane synthesized from propane itself. So part A, they ask you for the reagents and conditions. Part B, they ask you to describe the mechanism. And part C, they suggest the reaction condition required for you to have access of this fluoropropane. So let's look at the first one. State the reagents and conditions. When people is asking for reagents and conditions, you just tell them what is it that you need for this reaction. So I'll just write chlorine gas or chlorine, Cl, UV light. Okay? Then they ask you to describe the mechanism. So when people ask you to describe the mechanism, it just simply means write out the mechanism. There is no need for you to write lengthy words like what we did in our notes, because what we did in our notes is trying to explain to you the rationale behind each step. So when you're answering the question, when they say describe the mechanism, basically it's just to write out the mechanism. Okay? So for the start, I have my UV light with my Cl2, my initiation, UV light Cl2, so I get 2 radicals. Next, I move on to my propagation. Okay, so the Cl radical reacts with the propane. In this case, I get my propyl radical. Then I move on. Alignment, okay. Then I move on again to get my di-substituted propane. Okay, so this one would be the propagation step. So what you should be doing is to answer the question. The question say 1 chloropropane. So you show your examiner how you get that 1 chloropropane. Okay, then after that you move on with the 1 chloropropane, you go on to get your di-substituted, because that is also one of the compounds that they want to produce. Okay, and finally, And finally, you will have your termination. Okay, so termination got many. Just write any two. Okay, it's because of the radicals coming together. Okay? So you can just copy any two that you like, or you can just look at the video again later. Okay, while you are copying, can I give you a question, food for thought? Have anyone among you ever wondered why is it that I do not get a H radical? Or none of you thought about it? Has anyone among you asking your friends, why not a H radical? Why is it that I have a Cl radical? Why is it that I have a ethyl radical, propyl, and not a H radical? Okay, food for thought. It's more of the stability of the radical itself. Okay, so you can think about it. Okay, are you done? Can I move? Got video right. You all can get video right. Okay, next. Suggest the reaction condition required to have a large excess. So now I want a lot of this. So if I want a lot of this, I will have to have excess propane. Either one. Either you put a little bit of the chlorine or you put a lot of the propane. Actually, it's the same thing. Now the last one. I think just now at the very start, before we begin, I actually told you that F2 is very explosive, even in the cold and the dark. I also told you that I2 is no reaction. That's why we only work with Cl2 and Br2. I am not sure if any one of you ever occur in your mind why is it so, or ask yourself or ask your neighbor why is it so. Okay, the reason is actually because of the energy itself. Okay, so if you look at all the various bond energy that I have, okay, you will notice that I have a CH bond that is broken here, I have a HX bond that is formed here. So overall, I will be able to calculate the enthalpy. Okay, so I have already written out why I should have put HF, but never mind. HCl bond form is stronger than the CH bond broken, so reaction is exothermic. That's why it is able to proceed on. So for HF case, okay, the HF bond form is actually much stronger than the HCl bond that is broken. That is why the reaction is highly exothermic. And because of that, the reaction is explosive. Okay? So on the other hand, your HI, okay, if you look the values of the HI, only 299 as compared to the energy that is needed to break, you will notice that overall the reaction is actually highly endothermic. And because it is highly endothermic, it is unlikely that it will carry on. And that is the reason why I2 is not used in this free radical substitution. Neither do we use F2. Okay? Okay, this is more of the industrial application, more for your knowledge itself. How are we going to separate the different one? So in conclusion, when I talk about free radical substitution, I will say that it is likely that I will get a mixture of products, and it is very hard for me to control what compounds or what products I want to be formed, because it is so-called like a random, you will just substitute any H that is available. So it is rather a random substitution. So if you want to talk about the yield of a product by using this method, I would say that the yield is very low. Okay, so as you learn on further into organic, you will know that actually there are many other ways to get the products that you want. Okay, so this is just one of the many methods. Okay, this one, the next part that I'm talking about is actually more of the consequences of burning alkanes. This is very related to our everyday life, like for example your greenhouse gases, your greenhouse effect, okay, the catalytic converter, which I believe many of you would have already have quite a good knowledge of it. So for example, when I burn alkane, okay, I will have some incomplete combustion. So that will result in carbon monoxide, that will result in unburned hydrocarbon. Okay, or some there can also be a nitrous of oxides of the nitrogen due to the burning of the alkane. And all this actually have consequences to our environment. Okay, so this table is actually given to you, okay, to say that when there's incomplete combustion, what can I do to remove them? So in a catalytic, when I have a catalytic converter in the car, what I want to do is actually to remove the harmful gases, okay, convert them into harmless gases before releasing it out into the atmosphere. Okay, so I can have a few examples like carbon monoxide, I can have carbon, I can even have my unburned hydrocarbon, or I can have my nitrogen oxide. All these are actually gases which is harmful. So by placing a catalytic converter in my vehicle, I'm actually converting it into harmless gas as much as possible. Okay. So this is just a summary of everything, okay, where you can get it from, and yeah, okay, this is just for your knowledge. I actually have one video to show you to summarize all this greenhouse effect. Basically, I think this one I don't need to go through. A lot of you already know what is greenhouse effect. So we will end off with two videos. First video is about the greenhouse gases. The second video is about ozone. Okay, the ozone is actually the enrichment that you have. Okay, so let's end off with these two videos. We need to keep quiet to listen.
What happens to all that light, white energy after it reaches us here on Earth?
For me, they give you vitamin D, and for the tree, they help it stay alive.
When they hit the ozone layer, part of it gets absorbed, part of it goes out into space. It depends what's on the ground. Sometimes it reflects up into the air, and if you're standing on top, it might reflect onto you. But if it doesn't reflect, it just stays on the ground and it doesn't go anywhere.
In a way, they're all right. Some of the sun's hot rays are absorbed, warming up the planet, but a lot bounce back out into space. And on their way out, sometimes they get stuck. That's because they bump into tiny little particles floating in the atmosphere called greenhouse gases. They include carbon dioxide, methane, and nitrous oxide. It's normal for greenhouse gases to be up there in the atmosphere doing that. They're a natural part of Earth's climate system. In fact, without them, our planet's average temperature would drop to -18 degrees. meaning all the water on Earth would completely freeze over. So in many ways, greenhouse gases are great. You can think of them as being like blankets on a cold night. They trap more heat in to keep us warm. But what happens if we put on too many? Things start to get hot. And the same thing could happen with our planet. Unfortunately, our main energy sources like coal and petrol release extra greenhouse gases into the atmosphere. So by generating energy like that, it's kind of like we're putting more blankets on the planet. In fact, scientists say, thanks mostly to humans, greenhouse gases have risen to their highest level in 800,000 years. And that could cause some big problems. Climate scientists say it'll warm up the planet, which will melt ice, causing sea levels to rise, and that will threaten people living close to the water, and some animals will suffer too. More greenhouse gases could also cause our intricately balanced climate to change, meaning more extreme weather in the future. Scientists say if we don't start to bring greenhouse gases down to natural levels, the damage will be severe and irreversible. So they're calling on the world's governments to find ways to reduce greenhouse gas emissions. Compared to the levels in the year 2000, the Australian government is trying to cut greenhouse gases by 5% within 6 years. That's going to be pretty hard, so they'll be giving big businesses money to try to invent new ways to tackle the problem. And they're building a green army of young people to plant more trees, because trees actually drink in one of the gases, carbon dioxide. But everyone needs to chip in, and that's not just other countries, it's also you and me.
The Australian Youth Climate Coalition's 3 top tips for reducing your greenhouse gas emissions are 1. To ride your bike to school, 2. To buy less stuff, and 3. To talk to your parents about climate change.
Given scientists want us to completely stop using energy sources like coal and petrol by the year 2100, it might be time to get a roll on.
Okay, this one, the first one is about the greenhouse gases. The next video that I'm showing you is actually the ozone. Okay, this is actually on page 14 of your notes. It's actually enrichment, but I think it is good for us to know more about the ozone. Okay, to see how CFC actually causes ozone depletion.
Earth, a beautiful blue marble. Who would guess that serious changes are taking place in its atmosphere? These visible wavelengths are only a part of the electromagnetic spectrum. What you don't see are the radio, infrared, gamma, X-rays, and the sun's harmful ultraviolet rays, known as UV. So how does ozone play a part in this story? Ozone is a relatively unstable molecule found in the 3 layers of the Earth's atmosphere. In the stratosphere, ozone acts like a warrior's shield, protecting us from the sun's ultraviolet radiation. With the depletion of ozone, we become more vulnerable to skin cancer and cataracts.
Ozone is O3. In other words, the ozone molecule is made up of 3 oxygen atoms. Ordinary oxygen is O2. High-energy ultraviolet radiation in the stratosphere breaks oxygen molecules apart, forming 2 separate oxygen atoms. These oxygen atoms are highly reactive, and they quickly join nearby oxygen molecules to form ozone. Stratospheric ozone protects us because it efficiently absorbs ultraviolet radiation. The absorbed UV energy splits ozone into an oxygen atom and an oxygen molecule. The free oxygen atom quickly combines with a nearby oxygen molecule to reform ozone. We see that ozone forms, breaks up, and forms again in a repeating process. Because of this continuous repeating process, UV is absorbed by ozone and less reaches Earth. Because ozone is a highly reactive molecule, it interacts readily with nitrogen, hydrogen, bromine, and chlorine compounds. For example, when a chlorine atom collides with an ozone molecule, it steals an oxygen atom to form chlorine monoxide, and it leaves behind an ordinary oxygen molecule. When a free atom of oxygen collides with the chlorine monoxide, the two oxygen atoms bond to form an oxygen molecule. The chlorine atom is thus released and is free again, free to destroy another ozone molecule. This ozone loss sequence is called a catalytic cycle and is a natural process that has always existed in the stratosphere. As a result, one chlorine atom may destroy hundreds of thousands of ozone molecules before it forms one of other chlorine compounds and exits the stratosphere.
The level of ozone in the stratosphere is balanced between the production of ozone due to the highly energetic UV radiation and the loss of ozone by catalytic processes. This delicate balance has been upset by a five-fold increase of chlorine in the stratosphere since the early 1970s, causing the balance to shift to lower ozone levels. The chlorine increase has resulted from the chlorofluorocarbons, or CFCs, released in large amounts due to human industrial activity. Unlike ozone, CFCs do not break down easily. They are not water-soluble like most chlorine-containing compounds, which may be washed out of the atmosphere by rain. In fact, CFCs eventually are transported intact into the stratosphere, where their concentrations have been measured by NASA instruments.
In the upper stratosphere, the CFCs are broken apart by UV radiation, the first step in a chemical process that destroys ozone. The chlorine atoms are then freed from the CFC, and they can catalytically destroy ozone. Ozone depletion is occurring because the CFCs and other manufactured compounds are causing additional ozone destruction.
Originally, the ozone depletion process was based on theories. However, British scientists studying Antarctic ozone and NASA scientists gathering data from an ozone monitoring instrument in space were stunned in 1985 when they discovered that ozone had decreased dramatically over an area near the South Pole. We call this ozone decline and loss the ozone hole. Ozone depletion has occurred in both hemispheres of the world. Many countries contributed to the problem. Fortunately, most industrial nations have signed agreements to phase out many of the damaging chemicals. Meanwhile, the thinning of our protective ozone layer is a reality, and it adds to the basic danger of excessive exposure to the sun.
So we have come to the end of the lecture. The videos, if you are interested, I can upload it on the LMS. You can look at it again. Or you can just go YouTube to find. There are quite a number of good videos there. Okay, so finally, I would like to wish all of you your A's for your exams. Okay? I am sure you can do it as long as you put in your due diligence to get it done. Okay, so may the A's be with you. Wednesday there will still be a lecture on alkanes. Okay? You may go. Thank you.